So welcome to another class about the Branch spaces, and we will continue with a bit of the theory of hard spaces. Again, the previous lecture and this lecture, I took a detour, let's say, in the book. And then I'm using this guy here, John Garnett, and his very famous book about the topic. To do these notes. So in the last class, we defined the Hardy space as in this way here. So we are always defining on the unit disk and the upper half plane because they are linked. Often you can go in the book, you find, if you read it, you find some lemmas that tell you how you can go from one space to the other, but basically what you use is a conformal mapping, sending the unit disk to the upper half plane. It works in one direction, in the other direction you have to do some kind of tricks. But anyway, you can always go back and forth between these two spaces, so it's always nice to keep both in mind. And then what you usually do is simply you have an analytic function, and then let's say in the unit disk, then you have several units, circles of radii r inside the unit disk. And then you just take the LP norm of the function along these circles. That's what I'm doing here. And if the supremum is bounded, then you say that this function belongs to the HP, the hardest space of the unit disk. And in the same way, instead of taking circles, you take just lines parallel to the x-axis, and you take the LP norm if the supremum among all those LP norm is finite, and that's the Hardy space. Okay, so today what I want to show is that as we did for the harmonic functions, whenever so let me maybe go back a little bit. For instance, here, for harmonic functions, we said that U is always the Poisson representation of some function. If U is harmonic, for instance, let's say the real part of a function in the Hardy space, because we have exactly the same condition here. We're taking the LP norm along lines, and then the supremum is bounded. So, for instance, if U is a real part of a function in the Hardy space, this condition will hold, and therefore it would be representable by Poisson convolution with a Poisson kernel via an LP function. Okay. In the L1 case, it can be a measure. Okay, but then we rule out this later with the theorem we're going to show next. Actually, this measure here will end up being absolutely continuous with respect to the Lebesgue measure, and therefore we don't have to make this case distinction. So part one of the theorem will actually hold for less or equal. Okay, and this 3 is the Poisson representation of a non-negative harmonic function, which we already did, but we did using the Branges book. Okay, so the first theorem I want to write today is theorem D. And that is, I guess, it's theorem 1. This is theorem. I'm trying to see what the number is on the book. Yeah, this is theorem 3.1 in Garnett's book. So let's see, 1 less or equal than P less than infinity. And F belong to HP on the upper half plane. And then for some alpha positive, we define the following maximal function, which will be the sup of Z belonging to a certain cone of aperture alpha of f of Z, where, let me define what the cone here is, where the cone is just the Z in the upper half plane, so that x minus t is less than alpha y. Okay, so if you draw a picture, this cone would be, so if that is the real axis, and this is the point T, then we will have a cone here. And if this thing here is an angle theta, let's say this is theta, then a tangent of theta would be this alpha. Let me see if that's right. So if alpha is 0, which should have only this vertical line, that means alpha 0 means that the angle is 0, correct? Okay, so that's the cone. So what we're doing is basically just, so for each function in HP, we just take the supremum over this cone here and define that as the maximal function. So then this maximal function is a bounded operator from LP to LP. So it's, yes, so if I take the LP, let's say let P and on the line, that's what I mean. Well, the maximal function is only defined as a function for real T. HP, okay? So there is, for some C alpha, which does not depend on P, depends only on alpha, on the angle you're fixing to define your maximal function M alpha. Okay. And then if you had a course about, let's say, the back differentiation theorem, when you show that the maximal function is bounded and so on. So whenever you have a maximal function is bounded, means that pointwise a limit exists. And in the case of the back differentiation, we had that we could recover the function by taking average along balls. If the radii collapse to 0 of those balls, then you recover the function almost everywhere. And here is similar, but instead we're using cones to take the maximal function. So the next thing I will say now shouldn't be surprised. Shouldn't be a surprise. So in particular, the limit up. So we take the limit, 1z converges to t, and z belongs to the cone. So I'm taking points here and converging to t. That limit will exist. In particular, the limit exists, I should say the following limit. Exists almost everywhere and defines the function ft because it exists almost everywhere. And then this function will belong to LP of the line. The HP norm, which I use the same letter. If I want to be rigorous, I should use like maybe F star here to denote this is called, maybe I should already say, this is called the non-tangential limit because you're avoiding taking limits like this going in a direction that is almost tangent to the real line. That's why we select such a cone. Yeah, so that defines the function. The function is LMP. And if you take its LP norm, it's actually equal to the HP norm of the function f. Again, I'm making abuse of notation. If I want to be completely rigorous, I should put another name for this, but I'm identifying the limit with the function we started with the function f. And fx plus iy will converge back to fx, to this function we just defined. Well, if y goes to 0, we know because of the previous statement, the limit exists almost everywhere. So if I claim almost everywhere, I'm not saying anything, but actually this converges back not only almost everywhere, but also in LP of x and also almost everywhere as y goes to 0. Okay. And that thing here includes the case p equals 1, which is very important. And also in the book, you see that it actually goes beyond, and you can even put just p greater than 0, and it still will be true. Okay. And the reasons what I said, when the case p equals 1, you could have a measure, but then you show that this measure has to be absolutely continuous with respect to the Lebesgue measure. And then you have a proper L1 function, and then you can take, and then everything will work. Okay, so I'm not going to prove this theorem. As I said, I'm just briefly going to the background of the Brun spaces and the theory behind it. I just want to mention some results. If you go, the book is very easy to read. If you want to prove that, first you can prove that only for the real and imaginary parts. So that is, you can prove this theorem only for harmonic functions, the analog for harmonic functions. And that's even in the chapter 1, for instance. Okay. Any questions here in the statement of theorem?
Yeah, so this limit does not depend on alpha. We choose just alpha to exclude this tangential thing, but then it doesn't matter what value alpha.
It doesn't matter, yes. Yeah. For any alpha, well, yes, well, if you take a cone and you take the limit, okay, exists, and if you put a larger cone, then it has to be equal to the one in the previous one because it contains it.
Yeah. Okay.
Yeah. Yes, great. So, and then the next result will even contain, I think it's theorem 12 from the Brun's book, and it's one I will show, which is if 1 is less or equal than p less than infinity, f in HP, and we have its non-tangential limit, which we know exists now by the previous result, and is a function LP. Moreover, not only that, it converges almost everywhere and also in the LP to this function of x. Then f of z equals 1 over 2 pi I integral in R f of t minus w dt, okay? Which is also equal to its Poisson representation. dt, and if you use only the Poisson representation, and then this thing here, I should also mention, this last representation also works for p equals infinity. Okay, so this is corollary 3.2 from the book of Garnett. Okay. So let me prove that. So the idea is to use this epsilon trick as always. So we know, say from theorem C. What's theorem C? Let's go back. This was for the unit disk, but I wrote it. Yeah, C prime, I should say. That whenever you have an harmonic function in the upper half plane and we have a condition like this, if it's between 1 and infinity, I should say that actually this theorem here, I was not unsure if it works for p equals infinity, but after an inspection in the book, it actually works for p equals infinity, sure. Because we use the Banach-Alaoglu theorem to extract a subsequence which will work at infinity. So it also works here. But anyway, if we have this thing here, then we know we will have this thing for the real part of my function f. Okay, because we have this condition. So therefore, it will be represented by a function in LP. And in the case p equals 1, well, we know it has to be a measure. Okay, but since I'm doing the epsilon trick, this measure has to be equal to the function because the function will be continuous. So by theorem C prime, we have and then you do this for the real part of f and for the imaginary part of f, they both work, and then just add the formulas, the Poisson representation, and you get this. And this would work for 1 less or equal than p less or equal to infinity. Okay. And then now we use theorem 3.1, because when epsilon goes to 0, we have convergence in LP. Okay, if p is less than infinity, works for 1. And if p equals infinity, means is given by a, if p equals infinity, what do we have? Well, if p equals infinity, then we have to appeal to theorem C already. And theorem C already gives us that, because with p equals infinity, we know that is already representable by Poisson integration against the function in LP. And then we have to use theorem B. B prime will say what? That, which I only wrote the version for the unit disk, but I have it here. That if you have a finite measure, then it converges back in the weak star topology, okay? And that will cover the case p equals infinity, okay? So there is a version of this in the upper half plane as well. So when y goes to 0, we have to use then by theorem D, B, and maybe the prime versions of it, maybe there should be B prime here. We have the only thing I need is weak convergence, because I'm using this formula for y positive, and this thing here for y positive is in L1 as well. So the only thing I need is that this sequence of functions here converges weakly, a weak star, to the function ft, which I know exists by theorem D. So, and that we have. So that would work for p equals infinity as well. Okay. But then if I want to pass from this representation to this one here, then I can't put only infinity because this function here is not L1 on the line if f is just L infinity, okay? So then I have to restrict to the case p less than infinity. If I want to, so this would be Cauchy's representation, this would be Poisson representation. Okay, so then what we do is that we realize that this is 1 over 2 pi I t minus z dt minus 1 over 2 pi I on the line ft t minus z bar dt, okay? Because, well, the Poisson kernel would be the imaginary part of something, and then if you write what it is, that's exactly it, okay? But then you see that if p is less than infinity, then let's say, let me write this as, let's say, u minus v. So if p is less than infinity, then u is analytic. Because it defines an analytic function, because everything will converge nicely. This guy would be an LP function for p less than infinity, and this will belong to LP prime because p prime will be bigger than 1. Okay, so this would define an analytic function. So therefore, f minus u, which is minus v, so maybe I should write plus v. So f minus u, which is v, is analytic. But it's a function of z bar, okay? Conjugate of z. The only way this is analytic is if that is a constant. So that implies that v is a constant, okay? But then what you do is if you take the real part, you see that it will be an integration against a Poisson kernel, and then you can show that, well, because of that, this constant has to be 0. Okay, and you also have the condition, the condition that the function needs to be LP on lines and etc. Anyway, I will leave this as an exercise. Oops. And exercise. And thus v has to be identically 0. Okay. And that shows the result. We have the representation. Oh, they'll put W here. So we have this representation. And moreover, we got something nice. We got that. So this finishes. And an observation after that is that that 1 over 2 pi I integral of the line z bar dt has to be identically 0 for z in the upper half plane. Okay. Yes. Yes. Great. So one thing you can do to show that this function has to be 0 is just you do a Holder's inequality here to remove the LP norm, and you will have the LP prime norm here, and then you can estimate what this LP prime norm is. And then when you send y to infinity, this LP prime norm of this term here will have to go to 0, so the constant is 0. That's another way, maybe even a better way. Okay, any questions here? So, okay, so now we can go to theorem F. And that would be that the Hardy spaces are complete. That's the HP of C and HP of D are. Well, maybe before I say this, I should put another observation. Maybe I should number these observations. Observation 1, observation 2, that an analog of these two theorems, let's say theorem E, D, and E, an analog of theorems D and E hold for HP of the disk, and even more in the disk, since the boundary of the disk is compact, there's no problem with the infinity case. So you can even put infinity. And again, this can be also just P greater than 0. If you go in the book, there's no problem with that as well. Yes. Okay, so in the disk, if you're wondering, well, the non-tangential limit would be just the same. It would be a cone here, which not tangent to the boundary of the disk. That would be the limits you have to take. Okay, so now I can state theorem F. So HP of C plus and HP of D are complete. 1 less or equal than P less or equal than infinity. Okay, again, I can go all the way to just P greater than 0. Proof. So this again is very simple to do. I will, let's say, let me, yes, let me do it only in the unit disk. I mean, we can always choose and leave the other one as exercise. But the bottom line is that we'll have a representation. Okay, because now we know that we can represent our function by a Poisson integral. Either a Poisson integral or something like this, okay? So if I do in the unit disk, it will be better because then I don't need to differentiate between P less than infinity or up to infinity. And I can just use that already. So say, so I will show only for HP in D. Okay, HPD. Okay, so we have a representation. So FC equals 1 over 2 pi I integral on the boundary of f of I theta. So we should say maybe W here, Z, and the Z minus W. Because we know that the tangential and non-tangential limits exist. Define a function in LP, and in the unit disk, I can even put the L infinity. I don't need to treat it differently because, well, L infinity is contained in L1, for instance. So that's helpful. Okay, so we do have that, great, for some function in LP. So what we can do is just say that in W less than 1. So I can just say that this is less or equal than what? Then the LP norm of F in theta, which we know is going to be just equal to the HP norm. And then the LP prime of this guy in the boundary. So maybe I should put EI theta LP in theta. Okay, and as long as W is in the unit disk inside, any LP norm here is finite, infinity or 1, etc. As long as W is inside. But this function here is continuous inside. That's just something easy to show. So therefore, if you take any compact set inside, this function here is uniformly bounded. Okay, so this inequality is saying that if Fn is a Cauchy sequence in HP, now this inequality is saying two things. One, first thing is, what I should mention already, is that the functional evaluation, I'm evaluating the function at a point, is bounded, it's a bounded function because this is less or equal than the norm times some number, fixed number. For each W in the unit disk, this is bounded. So the functional evaluation is bounded. The same thing will hold for the upper half plane. Okay, not only that, if you have a Cauchy sequence Fn in HP, then Fn is Cauchy in, let's say, L infinity of K for any K in the unit disk compact. So for any compact K. Okay. So therefore, we know that Fn will converge to something, just some analytic function in the unit disk. So that would imply that Fn converges to some function f uniformly in compact sets of D. Okay. And then we know that, well, then it's just a matter of applying Fatou's lemma. If you have Fn minus Fn, and I do say the norm HP, okay, I know that this is less or equal, I should do just to be careful. Let's see, REI theta minus Fn REI theta. And I do LP theta. Okay, that's going to be what? That's going to be less or equal than the limit inf. This is Fatou's lemma. When m goes to infinity of Fm REI theta minus Fn REI theta LP in theta. Okay. So in this case, I should say P less than infinity. Oh, this also works for P equals infinity, no? Because, yeah. For P equals infinity, it would be even like it would be like equal to the limit. So I don't need to say that. Or should I? Yeah, should I say? Let's separate the cases to be clear. Then by Fatou's lemma, have this. Great. Okay. But then what happens is that this guy here is what? This guy here is definitely less or equal than the limit when m goes to infinity, the limit inf of just Fn minus Fn and the norm in HP, because the norm in HP is the soup of Mongol DRs here. And then we know it's a Cauchy sequence. So we do know that this thing is going to 0. So if I take the lim sup in both sides here in n, with n going to 0, this bit here would be a lim sup and n goes to infinity, sorry, n going to infinity. Limit sup when n going to infinity, and limit inf when m goes to infinity. But since this is a Cauchy sequence, that's going to converge to 0. So that implies that the limit when n goes to infinity of this is that what I want to show? Okay, so first of all, we do have this. We should do first something. We have this, but the right-hand side now doesn't depend on R. Okay, then we take the sup in R. So that would imply that F minus Fn HP is less or equal than the lim inf. M goes to infinity. Yeah, we should do that first. Okay, but this is converging to 0 as n converges to infinity. And that would finish. If p equals infinity, so we'll have to take the sup in theta. That's gonna still work here. Let's say, suppose the p is infinity. So we're gonna take the sup here, which is gonna be less or equal to that. Sup in theta, I could still do that. Yeah, I don't see any problem doing that. Let's see how it does in the book. Yeah, does it very simply. Assume p equals less than infinity. Okay. Yes. Okay. What? Yes, I guess we can always assume, yes, in the book he says that we can always assume that p is less than infinity. I think because L infinity is contained in L1 because of the obvious inequalities. And therefore I could do, if it's L infinity, I could do LP, I could do the exact same estimates. And then I would get this inequality here for every p yeah, so this inequality is saying that for m sufficiently large, this works. But then if I take the supremum in p, what's going to happen? Send to p to infinity, let's say, then this is going to converge to the L infinity norm. Stereo. Yes. Yeah, so the same argument would work. Okay. So I would leave as an exercise. Okay, I don't see any problems. You can assume if it's L infinity is an LP, you repeat everything, then you get this final inequality, and then you send P to infinity, and it should work. If it doesn't work, then you let me know, then we work it out. But I think it's going to work. So now HP and HP is always a complete Banach space. Great. What else can we say about it? Any questions here in this thing? Okay, so I have a bunch of observations to do now. So far what we have, let's review. We have these Hardy spaces, okay? And we know that there is always a non-tangential limits. So there is always a function on the line or either in the unit disk, in the boundary of the unit disk that represents the function via Poisson integral. And this works for every p. Oops, technical problem. Okay, so it works for every p. And great, so you have a boundary function. And moreover, we have Cauchy's formula or either the Poisson representation for these guys. Great. So we have some nice Banach spaces, and they are used in several parts of analysis, in harmonic analysis, or even more like complex analysis kind of stuff. What do we know about these guys? What else is those? I will do a series of observations here. So the first observation is that, for instance, there's a numbering, so there will be observation 3. So observation 3 would be, well, if you do this norm, P of x, this thing has to increase up to the norm of f on the real line when y decreases. Yeah, because that's, well, we already saw that once we have this representation here, then a simple Minkowski inequality tells you that the LP norm in any line loses, is less or equal than the LP norm on the real line, okay? But then if you do the epsilon trick, if you write f of z plus I epsilon and do the same thing, that would imply that any norm above the line imaginary part equals epsilon. Let's say this is I epsilon. Any norm in the line here will lose to the norm in here. So that would mean that the function is increasing. Okay, that's sometimes a nice property to use. The same thing works for the unit disk. What is supposed to be T? And the same works if you just use the real or imaginary parts. The same result works for harmonic functions, as long as here is in HP and here is in HP of the disk. So observation 4 would be what? Yeah, as I already said that the theorems had a similar result in the unit disk. What else? Oh, yes. So if you go to the unit disk, then this will be the closure of polynomials. In case if you get polynomials in the unit disk, and HP is always the closure. And the idea is very simple because if it's, well, I will show you two things simultaneously. If you just expand your function f as a power series, okay, then what we know, then we do know that what? We do know that the limit when r goes to 1 of this of the theta goes to 0, but that is to say that, when we expand our function, the boundary function, as a Fourier series, So that would be the boundary function. And we modify it by multiplying by r less than 1. Okay, then this goes back to f of ei theta, the boundary function in LP, in almost everywhere, when r goes to 1. Okay, so one could say that, in this sense, one could say that okay, it's a bit more technical to show that I think one piece between 1 and 2 that actually, yeah, this, if you truncate this series, then it converts back to the function. But what you can do, so I didn't show that this is polynomials yet. I just showed this, but since we know that this is true, then what we can do is simply realize that, well, for every, let's say for every capital N, there will be some r pretty close to 1, but less than 1. So that I should say for every epsilon, there would be what? We should say otherwise. I should say for every epsilon, sorry, every epsilon for every r less than 1, there will be some number n, so that if we do this and we take the sup moduli of z less or equal to r, this would be less than epsilon. But that is true simply because the power series here converges uniformly to f in any disk with radii less than 1. Okay, so I can always do this. I can always select this n so that this is less than epsilon. Okay, so that would mean what? That would mean that if I go back to this inequality here, to this limit, and replace by this approximation, then we get what? Then we get the limit when r goes to 1 of the integral, maybe the limit sup, and I should say, let's say any r. It also depends on epsilon, but I'm fixing epsilon for the moment. That would be r to the n, e to I n theta minus f of e I theta, key the theta. That would be less or equal. Then we'll have to do LP to be. Since this is less or equal than epsilon, you just add and subtract this term here. Yeah, so you have this, so just add and subtract this function here in this limit, then this part will go to 0, and the other part will be by this bound less or equal than epsilon. So this would be less or equal than epsilon. Okay, so an epsilon can be anything. So that means that you just found a polynomial. Okay. So what is this here? You're taking the limit, but you know, yes, you're taking the limit. Yes, this is just the, this is approximating. So this is a polynomial. So this is the same as, so this is the same as doing the norm of what? This is just r a n z to the n. 0 to nr. So this is a polynomial p of z. Okay. And we're just doing the boundary norm, the norm on the boundary of something. So this is just, so this thing here is just p, let's say p of r. P of r ei theta minus f ei theta norm LP, okay, on the boundary. But since they are function, or any polynomial is a function in the Hardy space, in any Hardy space, so therefore we know that this is actually equal to PR minus F HP, okay? And I'm saying that I just found a polynomial, PR, so that, yes, it's limit sup when r goes to infinity is less or equal than epsilon. So this is pretty close to F in the HP norm. Okay, so this shows that the polynomials are dense in HP.
Excuse me?
Yes.
Why do you have equality here and not an inequality?
Oh, in the last one?
Yeah.
Yeah, so, well, a polynomial is in a Hardy space. This function is in a Hardy space. And then we're doing just the norm and the boundary. But we show that the norm in the Hardy space is actually equal because it's increasing. This was the previous observation. It's increasing as a function of the radii. So this function here, which is just a norm on the boundary, has to be equal to this. Because if you do any smaller radii, let's say moduli of z equals t, okay, by the previous inequality, by the previous, and you take the sup among the t's, by this observation, well, the sup is going to be equal to the norm on the boundary.
Okay.
Yeah, so we did all this work just to realize that whenever we do the norm in HP, that would just be the norm in LP of the function of the boundary. Of the boundary function. So that would be just this on the boundary, and this for the Hardy space and the upper half plane and on the unit disk. And that would be the non-tangential limit. So in a way, we're saying is that the Hardy space is isometric and isomorphic to a closed subspace of LP. Okay. So that would be the other observation. So thank you for the question. Observation, what? 5. That HP of C is isometric and isomorphic to a closed subspace of LP, okay? And the same thing for HP on the disk. We just showed that. Because its norm would end up being the norm of the boundary function. So, and whenever you have the boundary function, you can reconstruct uniquely a function in the Hardy space, okay? So that is one of the main results in the theory, that you have these functions on the upper half plane, and you have certain LP norms. When they are bounded, it just means that you can represent them by Poisson. Convolution with the Poisson kernel. So that begs the question, what happens in some particular cases? So for instance, so we just show that in the disk, since the functions are analytic, the boundary function has a kind of Fourier expansion, Okay, so that would be the Fourier series of a function. But if you recall, Fourier series could also have n negative. Okay, and what this thing is saying is that no, really, it has to be only greater or equal than 0. Okay, so you could ask what's the analog of this thing for Hardy spaces, and there is one, which is the following. So it should say, maybe I should say already, H1 of C plus is equal in the sense it's isomorphic once you identify the space with the boundary function, with the function on the real line, to the functions in L1. Maybe, I don't know, what's the symbol to say these two things are isomorphic, something like that. I don't know, let's say something like that, just creating that, I don't recall. Functions in L1 such that the Fourier transform is 0 if S is less or equal than 0. Okay, so if you think about the Fourier case is just, when you take the Fourier transform, well, you can only evaluate it in integers, so some way it's discrete, but the negative integers, the Fourier transform at that point is 0. And similarly, in here, it's the same thing. You take the Fourier transform, and the Fourier transform will be 0 if S is less or equal than 0. Okay, so how can we show that? Well, first of all, if F belongs to H1, then what? Then F of Z e2 minus 2 pi I S Z also belongs to H1 if S is less or equal than 0. Because when you do the moduli of such a function, you only depend on the variable y of the, and then you have like S times y, but S is negative. So this exponential will be less or equal than 1 in the upper half plane. So you're not changing anything. You're just like putting more of a decay in the function. And moreover, F of Z is less or equal than what? We showed this inequality before. The H1 norm times the H infinity norm, the L infinity norm on the line of this. This is by Cauchy representation of the function. But this is exactly equal, there is a 1 over 2 pi at some point, 2 pi here. But that's exactly equal to what? If you do this norm, this L infinity norm would be just the y part of it. So it will 1 over 2 pi y, the norm of f in H1, okay? In particular, the function is bounded. If it's bounded if z goes to infinity away from the real axis, okay? Uniformly away from the real axis, okay? So what you can do is the following: the Fourier I should define what's the Fourier transform. I didn't. Did I find? No, I didn't. So the Fourier transform is what? That's the Fourier transform of a function. If f is L1, then everything is well defined, etc. And I want to show that this is 0. Okay, but since I just showed that by this comment that f times the exponential is to a function in L1, maybe this should be replaced. Yeah, put this thing below and this thing above. Okay. If f is less or equal to 0, so that is, let me put a capital F here. Went too fast. So this capital F is still 0, and this is just the integral of f of t. Okay, so I just need to show the bottom line, just need to show that the integral of f of t dt vanishes for every f in h1. Okay, so that would show that this thing is contained in here. That the norms are equal, we already know. We just need to show that this thing is contained in here and that this thing is contained in here. Okay. Great. Then we use this inequality here, and we have that. So what we can do to compute the integral, so we just need to show that the integral vanishes now, and then since we have this inequality, what we can do is we can do the following computation. So 0 is equal to what? Well, that is definitely equal to, if I integrate the function on the boundary, intersect on the upper half plane, and integrate f of z is z. So what I'm doing is I'm doing a counter integral like this. This is minus r, and this is iy. This is the real line. So I'm doing a counter integral like this. So that would be integral from minus r to r of f of t dt, which we want to show it converges to 0, plus what? Plus something which is like r. There would be a integral for, let's see, this, there must be an I at some point here. So that would be what? That would be from 0 to 2 pi f of r e I theta. And then we have a I e to I theta d theta. Okay, so bottom line, we have to show that this piece here converges to 0. Okay, so we have to show that this piece converges to 0, but this piece will converge to 0 . So this is less or equal than r, integral from 0 to pi, moduli of f r I theta d theta. And the question is this converging to 0? But then you realize something. Do you realize something? Well, I only need to show the result, which is that the integral of any function here is 0 for a dense class. Because if I show for a dense class, dense in the H1 space, then that result will follow by density because this is just the integral of a function. So if I have another function which with integral 0 that is close to in L1 norm to my given function, okay, then in the limit I will show that this converges to 0. So I only need to prove the result for a dense class. And once you realize that, then you can always force this limit to go to 0, for instance. So if I define f epsilon of z equals, for instance, this guy here. Okay. Then I know that f epsilon of z, let's see, r e I theta is less than what? We have this inequality, which I will use, and we have an extra r squared here. So maybe I should even put an r here. So we have something like 1 over r, which will come from this factor here. And then we will have this inequality here. But since it's plus I epsilon, I can just bound it by 2 pi epsilon. And then here, H1 norm. Okay, this is by the previous inequality here that we showed. Okay, so if instead of f, we had f epsilon, in all these calculations, we would conclude that this limit is 0. Okay, so that would imply that the integral of f of epsilon t dt minus infinity to infinity is 0, because this limit here is now bounded by this. When r converges to infinity, it converges to 0. So redo the argument with f epsilon and conclude that. Great. But then f epsilon easily converges back, but since f epsilon converges to f in H1, or even if you wanted to do the L1 norm on the line, then the difference has to converge to 0. Then we conclude that the integral of f of t dt is 0. Okay. And that's how Garnett does in the book, actually. He actually puts an even nicer class of functions, and then, which is always dense and always decays at infinity. And then he uses, he proves the theorem there, and then the result follows from density. So that would show the first inclusion, that this is contained in here. And the second part is basically the same, but that's actually a result, so I will state it. So the second part, the part where H1 of C plus contains the F such that F hat of S is 0 for S, let's say equal to 0. That is what? That is theorem. That is theorem. 3.8. Yes. Okay, and it's relatively simple to show because once we have that the function is its own Fourier transform, and then it vanishes, I can even give an idea. Once we have that f of x, once you show that you can do that, but that's supposed to be plus, yeah. So when s is greater or equal than 0, I can, oh, this is x. I x, let me keep the variable t, 2s, x, s, and s. Okay, so that's the Fourier inversion. So so yes, that's what we have. So if I replace x by z, you can ask, well, is this thing still gonna hold? Yes, well, let's see. If we take the moduli here and this function inside here, that's going to be something like e 2 pi I x plus iy times s. So it'd be e2 minus 2 pi I 2 pi y s, but as s is only positive, okay? So this is actually, if y is greater than 0, this is actually adding a decay on the function. So yes, you can extend this function as an entire function, and this identity has to hold, okay? So that's the basic idea. You can go in the book and look. Okay, so another observation that I would like to make. Any questions here so far? Is the space H2 of the disk. So we saw that H2 of the disk, we had this connection Fourier series. But if you think about, well, H2 of the disk would actually be equal to what we did before, then you can conclude that F0 of the disk will be the functions which have a power series and the power series is square summable. Okay, because, well, we saw that the boundary function will have this representation. Okay, in the sense that I explained before, but these functions here, but we know that this is an L2 function, but yes, this is an L2 function. So therefore this thing here, but by Fourier series, these functions here are orthogonal. Okay, so so what you can, so this would imply that Zn is orthogonal basis of A2 of D, because, well, A2 of D is about analytic functions inside, so that's why we have to use Z to the N. But since it's isometric to its boundary values, and its boundary values will be functions which can be expanded in this form. But since we are in L2, these are orthogonal and form a basis of the space, orthonormal even. So therefore, from there, you can conclude that these functions are orthogonal. And moreover, if you do the inner product, well, what is the inner product between two functions, f of g, let's say in H2? Well, by the identification with the function values and the boundary of the unit disk, this has to be this. Okay. But then if you do that with the expansion of f as functions on as power series, that would be exactly this. Okay, because well, this will be that, and then using the fact that this can be expanded as this, using in the sense that when I put R to the n and send R to 1, this converges back to that in L2. So if you use that conditioning there, then you will see that this identity holds. So therefore, this space H2 equals that. Another identification would be just take another identification would be maybe H2 of D is you can identify with the ANs such that, let me use the standard notation, identify with the L2 of, let's say, the natural numbers. Okay, and the way you identify this, you just take a function expanding its power series and then just match this sequence of coefficients. And that's another identification. Okay, so this carries a lot of structure and etc. One thing you can think about is that now that you have L2, let's see what time is it? Okay, now that we have L2, we know that, well, f of z equals what? Equals integral of f of z divided, let me put a 2 pi I inside here. let's suppose W minus Z dz, which you can write it as f of z. This is on the boundary of the disk, which you can write it as f of z 1 over 2 pi I, let's say z minus w bar, and then you put the bar in everything, dz. So that is just the inner product between two things and kw of z is just 1 over 2 pi I z minus w bar. So this would be the reproducing kernel. And the same computation will work in the upper half plane, and the same function would be the reproducing kernel in the upper half plane. Okay, so again, we have a structure of a Hilbert space with a reproducing kernel, exactly as, for instance, the LV spaces we defined, and exactly as we will define later that the Branges spaces will be of this sort, and this identity here will be imported. Okay. And I think I'm finished. Any questions, comments about everything?
So are all these spaces actually isomorphic then?
What spaces? Sorry?
Or the Hilbert spaces with a reproducing kernel?
Oh, if they're separable, I would say, well, it depends on what you mean by isomorphic. If you have two Hilbert spaces and they are separable, they'll always be isomorphic because you have a basis. But the mapping could be just a mess and don't reveal anything about the structure and properties, special properties about each one. In this sense, it's a natural mapping, and then, yeah, they will be isomorphic, but any other two reproducing kernel or Hilbert spaces will be isomorphic as long as they're separable, but maybe you don't know what happens with the kernel. You usually want an isomorphism that takes one kernel to another. And I would say that maybe they are, if you have some properties about the basis, then you can maybe map one kernel to the other. I don't know. I don't know exactly what you mean by the
I actually did mean that, like, mapping one kernel to the other will give us an well, hopefully an isometric isomorphism, but that's probably a bit much. But yeah, the question is whether we will always find a mapping between kernels, which will give us, in the end, an isomorphism.
I don't know. Maybe yes. I don't know. I'm not sure. Right on the spot, I have to sit down and think about it and give a better answer. But I would say my guess would be no, but it could be wrong. But anyway, good question. I will get back to you maybe in a email or something. Any other comments before I stop recording? Great. So thank you and see you next time.